If your team is setting up a lever and your job is to do, you're doing a first class lever. So first you got to build it. You got to kind of create something. And remember from way back, if you don't remember this stuff from 8th grade or even when you were building those things last year, it's really important when you're doing an axle, you get it going through two points of contact so it doesn't wobble like crazy. Just remember that with your, what is it, the Automa things when you were doing the cams. And then putting them on these little black bearings so they spin nice and smooth. Ideally, we want to reduce as much friction as possible so it's not as much of a play. All right, so the next thing you do, all right, so you build your system. You're going to have to, so that everybody ends up with kind of the same, we need a force resistance and a force effort, right? You're going to need to label that so that when the other group comes over, they know where to put them. So do we want this, do we want to put our effort on the long or the short end? You get to put your effort on the short end?
Oh, no, you want it on the long.
It's just going to give you you could do that. You're just going to have a mechanical advantage less than one, right?
No, I mix those up.
All right, so let's just say I'm going to stick it here. And then I'm going to put an arrow pointing so that I have it, so like I know that I'm putting it on this hole here. Right? Just so that everybody's in the same spot, because I would like to be able to compare everybody's answers. You know, group A, B, and C, what'd you get for deficiency on this? So when your group comes over, you got to know where to apply your effort, right? All right, so force resistance, do something like this, pointing to like, I'm going to put it on the end one for this one, just so we know. Cool? Okay. So the first step that we want to do is we want to know what the ideal mechanical advantage on this is. So this is where I want you to add into your notes. We're going to, if you look in that packet of papers I gave you yesterday, you don't have to do this right now. I'm just going to show you. This is going to walk
I got
you
it.
through.
No, don't pick it
Look at what it's gonna
up.
have you
Just
do.
keep it there.
It's going to say, go to the first class lever, do a little drawing of it, find the ideal mechanical advantage. Make sense? We're going to do this right now on this one, and then I'm going to have you guys do that process. So I'm basically giving you an example one so you can come through. So the first step, can I borrow this just so I look at it? I don't want you to write it in the packet because you're going to use this one for when you do the other example.
No, move your head.
The first thing we're trying to do is find the ideal mechanical advantage. How do we find ideal mechanical advantage?
No.
What's that?
Distance.
Right? Distance effort over distance resistance. How do I get the distance of the effort? I got to measure from where? From the fulcrum to where we're going to apply it, right? So you're going to have to come in here and you're going to have to actually measure what that is. And make sure you're coming, don't like run it up, try to get as accurate as you can to the pivot point. These should be pretty even measurements. It looks like I got 7.5. So 7.5 is your DE.
Yeah, I should take up this job.
All right, so what's our ideal mechanical advantage? Our distance to effort was 7.5. What else do you need? Okay, the distance of the resistance force, right? Which will be 3. So what's my ideal mechanical advantage? Okay. So the first thing you're going to have to do, it's going to ask you to sketch it. So you'd end up with like something like this. You'd have a force resistance. You'd have a force effort, and you'd have a 7 point. You'd have something like this, right? Like if we were trying to sketch that out. So you came up with an ideal mechanical advantage of what 7.5 divided by 3 is what? 2.5, which means if I've got 2.5 pounds here, I should only have to lift up with 1.5 pounds here, yeah? Okay. So we know our ideal mechanical advantage. Now, what we want to do is we want to figure out the actual mechanical advantage of this system. The first thing it's actually going to ask you is ideally how much effort would it take to overcome the force. We don't know what the force is yet. everybody's gonna create a force on theirs. And this is gonna be the force for this particular one. There's some weight here. But we don't know what that force is, right? So here's what we gotta do. Noah's gonna do this for us. Noah, if you scroll up so you can see all the apps on your Chromebook. Yeah, and now slide that thing up so you can see all the different things. There you go. You're gonna find one in there called Veneer Graphical something like that. Or, I'm sorry, Logger Pro Graphical something.
Oh,
That'll work. Okay.
I don't care if she gets out. Like, that's her problem.
Alright, so everybody on their Chromebook has this piece of software, and we've got these different different sensors that'll work with them. And I should have untangled that because that's driving me kind of crazy. Did that load yet? It's kind of looks very good. So the way these work is everybody has, like you plug this thing, it's called a GoLink in to your USB port, and then we can plug different sensors in. Now this particular one is a force sensor. I've got temperature ones, and I think you can get them in a bunch of other ones. So, did that load yet for you? No?
Yep. You did.
You're in
How do I get that part to go away? Oh, there you go. All right, plug in your GoLink. Plug in the force sensor, so we're kind of all connected together. I may have to come over by you and look at it because it's been a while since I've seen it on your end. Yeah, it would have been nice.
Just hit the angles.
It's different this year.
Why are you laughing?
I'll get that from up.
Because I'm trying the video.
Oh, I want this
Owen.
veneer graphic. I'm sorry.
Oh,
Not that one, that's why.
Yeah. What?
You're doing a great job.
He is.
I'm taking this up as a profession.
You probably should.
You can't see the computer.
You can't see the computer when you videotape
It's about 60% of the way through.
He's alright. He's alright.
Joe, what is that noise?
See?
Hey guys, it's me, Mario Kart fan.
Jesus. Not again.
Yeah, Joe, zoom in.
Yeah, but like, what's the point?
Perfect.
Oh, there she is.
Alright,
Perfect.
so he's gonna come up here to collect. Oh, that's not what I
That's
want.
it. Alright.
You're blocking your view.
Oh. Mr. Mackey, do I have permission to hurt a student?
To what?
No.
Hurt the students. I'll just wait for after school.
Oh my.
I feel scared. I feel scared. Scared.
Oh, are you good? Can you see? That sucks.
Who had shoes on that already? No, it's just
That's what said on the way.
Joey, you can't see anything.
Move your Beavis head out of here.
Yeah, see, mine was like blue. Well, mine had checkers.
I might have to play around with
Yeah, see, mine are just cooler.
I can't deal with him. I can't deal with him.
What did you say?
That's a pretty good picture of us.
I know it is. How do I get that?
Where are you?
Jim's right there. He had a mullet then.
No, that was after mullet.
Oh, that was
No, that was after.
Joe, I could see your mullet.
No, that was after. I remember.
No, it wasn't.
What?
Wait, is that hair or is that dirt?
That's both.
No, that's dirt.
Alright.
Sorry, Alex.
What is that noise?
No, this is dirt. What?
Yeah.
Show the camera. Show the camera.
How long is that video, Joe?
Like 9 minutes and 39 seconds.
Oh,
Mr. Mackey, you're gonna be at storage.
You'll be alright.
oh snap.
Alright.
The big one.
So go ahead and swap that sensor into my laptop for now. I'll sit down during I'm gonna need to sit down during like an RP with somebody's Chromebook and figure out how to make it so that I can show you guys.
Oh, shoot.
So he's plugged that guy in there, and we should be able to see, and I know his was reading right because it was telling me it was 1.28 newtons. So what we're looking for, we don't need it over time. We just need to know like what that force is actually sitting at. But what we want to know is what the resistance force is going to be. So you're going to take your force sensor, kind of hold it up here like this, and we need to zero it out. So come up here to, is it data or analyze? One of these, might even be just right here. What's this little
Collect.
next to it?
This?
Yep.
Click on it.
Yeah.
Set 0 point.
Go ahead.
So I can double click it.
It didn't seem to do it. Because what I wanted to do is I
Oh,
wanted
it's
to,
on.
there we go. I wanted to read 0 from the set point, or very close to it.
Yeah.
Oh, it's on 0.
So that when we pick this up, we can see what our actual force is going to be.
8.7.
Okay, so we're talking about 8.76 newtons per 0.7, and you got to hold it real still, and it will bounce a little bit. So we're trying to look for an average there.
8.7.
All right,
Oh,
so we'll go
okay.
to, so if we know our force resistance is 8.7 newtons,
Negative?
What does negative do?
if you know your resistance force is 8.7 newtons, how hard should we have to pull to lift that?
8.755.
Like
2.5.
It's that moment of force thing. We got to set all the moments of force set to 0. You could do it that way too because there's only 2 forces.
8.7 divided by 2.75.
Where do you get 2.75?
That's what he told me. That's what the IMA.
When have you ever listened to Owen?
The IMA.
Yeah.
Are you in freak out?
She's an honors freak out though.
Are you smart?
Oh, boy.
Lauren, are you smart?
I'm just better than everyone else, that's all.
Aren't you an honors freak out?
Chill down.
Carson and Alex honors freak out.
Better than everybody.
I'm joking.
Joey, up there. Joe, you're failing.
I can't even see it.
I know.
All right. Here's how you make that estimation. Set the moments equal to 0, right? So you've got a counterclockwise moment that's positive, 8.7 times 3. A clockwise moment that's negative, negative effort force times 7.5 equals 0. So I need help on this. I don't know what 8.75 times 3 is. Okay.
Pre-calc.
So subtract your 26 over, take that and divide it by 7.5. It should be,
I don't know.
yeah, about 3 point something. What do we got? Who's got a calculator?
What are we doing?
Negative 26.
We're trying to solve for FE, so
Negative 3.48.
Hurt me.
divide both sides by this divided by that. 3.48. Okay, it'll be positive because this is negative and this is negative, so they'll cancel. So our effort force, what we should need is 3.48 newtons, right? That's what we should need. So the question then becomes,
I know, I was just taking a little picture of the thing. Not picture, but like a little longer at the equation. She might need
so
help
the
with it.
question becomes, what is it actually? How hard do I actually have to pull down on this to make it happen? It should be 3.48. But it's likely a little more than that.
Mm-hmm.
Because actual mechanical advantage is going to be less, it's going to be a little less than the ideal mechanical advantage. So no, I'm going to ask you, now we're going to measure it to see what it actually is. Can you re-zero this thing?
Sure.
It is important to zero these things frequently.
Alright, on 0.
Okay. So I'm gonna take this thing and try to, can I hook it on there? Thought I could.
Sure.
Now I'm holding this and I'm trying to hold it at static equilibrium.
Alright, it's about 3.3.
3.48.
3.33.
So if we're saying it's 3.3, but we said it should be more than 3.4, right?
Yeah.
Okay. That's okay. We're gonna go with this number for a minute, 3.3.
Camera work, am I right?
It might not be leveled perfectly.
It wouldn't matter if it's level, it just matters if
According
it's
to the
equal.
force.
Because as long as, well, actually, that's sort of true. If it's level, I need to be pulling straight down, not pulling at an angle. But if I was down here, as long as I was pulling perpendicular, I should be okay. However, so there's gonna be some reasons why this is different. We'll discuss them in just a minute. All right, so let's leave that alone. Let's come back over, sit down for a second, so that we're kind of spread out, and let's crank that down. So we figured we already did our IMA, which is what? Nice. Beautiful. I don't need that projector on it.
Yeah, how do
We did our IMA, and we said it was what? 2.5. So ideal mechanical advantage is 2.5. When we sketched this out, we said ideally, our effort force is 3.48. Why is that ideal? Because we used the distances to figure out what it should be. Right? We didn't actually measure what it was. Even though we guessed what the force was based off of distance, based off of the measured dimensions. So that's an ideal what we think it should be. However, what it actually was, what did we say, 3.3? So what's our actual mechanical advantage? It's the force resistance over the force effort, right? 8.7 over 3.3. $2.6. How could our actual mechanical advantage be bigger than our ideal? Should it be? No. It shouldn't be. Because look at what would happen if we calculated our efficiency. Our efficiency is going to be the AMA 2.6 over 2.5 times 100, right? What's the efficiency come out to? It's going to come out to like 105 or something like that. $104. How could you possibly have an efficiency of 104%? Yeah.
We didn't have a good enough distance.
Okay. Here's. I'm gonna come on back around this thing. Leave your. If you need to write something down, come back around. We're gonna discuss why that actually came out like that. Alex alluded to it big time yesterday or the day before. The biggest contributing factor. I've got a pretty small model here, right? It doesn't seem like much. Okay?
Yeah, it's a calculator.
It doesn't seem like much, but I should be putting, we think I should be putting more than 3.3 newtons of force into this, but I'm not. Part of the reason is because the mass of this beam compared to the mass of this beam, it's almost 3 times heavier, right? So I'm getting additional effort from the weight of this thing, which is, I should be losing some in the friction over here, but it's the weight of the beam that's throwing me off. The first time we ever did this lab, we really struggled because we made the beam out of this, And it doesn't seem like much, but the comparison of weight on this compared to the amount of weight that we really threw on the end of this thing is quite a bit. The other thing about these things is, so we can get closer measurements. We've gotten better numbers. We found the trick to getting better numbers is using as much mass as we can get away with, so that our forces are a lot higher in comparison to the mass of our beams. The downside of that is these beams aren't super strong, right? So I've had problems where like we start doing stuff like that and then we try to pull down on this and that beam wants to deflect or bend or do something like that. So that is the downside of that. So what we try to do is, and that's why I've got so many of these weights on there, we try to get more weight on there within reason, because these will only measure up to 50 newtons. But if we could have gotten, let's say our force resistance on there somewhere up around like 30 newtons, we would probably have gotten an efficiency down where we believed it should have been, somewhere under 100. Does that make sense? So if you get an answer that doesn't make sense, here's a part that I really care about. If you get an answer that doesn't make sense, we shouldn't have an efficiency. But if we got an efficiency like that, why would it happen? Because if you can justify why, I'm cool with it. I don't have a problem with it. I just get really annoyed when you say, oh, it's efficiency of 110. That doesn't make sense. Why did that happen? You say, I don't know, that's just what I got. That's the part that's not good enough. Cool. And the very first time we took this lab, it took us about 3 days to figure that out. And I was just like pulling my hair out, because it was like, how the heck is this? Why is this? Because I knew an efficiency of 100 was not possible. And it hit us like 3 days later. I forget what I was doing. I wasn't even doing, I think it was just like driving to school or something like that. So if you look on the outside of that door, there's a nice vinyl sticker that says the weight of the beam from the iron plate. It's pretty nice. They made it for us. I think it might have been Paul. Okay. Does it make sense what we're trying to do? Okay. Cool. You can kill the video, Tao, because it's not really important.